So what I want to do today is walk through a few things. And the first thing I'm going to start with, the first thing I want to start with is today we're going to transition. Last time we built a model, which is shown here. And that model was all in numbers. And it reflected a flat top dipole, which we're going to re-review. And we played around with it a little bit. We showed how to get SWR sweeps, how to get the gain, and a few things like that. And then I had asked you guys to go off and build your own model. As I mentioned, I think that was a mistake. We spent too much time on that. But assuming that this is where we were, assuming you built this model, you've had a chance to use it. It's composed of the wires, of which there were 4, the left leg, the right leg, a center element for the transmitter, and a mast. So it's a very simple model. We had a ground card. I left the scaling in there, but since it's in meters, the scaling is 1.0. We discussed the loading for copper wires, the transmitter, an EX card, and then a frequency card. So a very simple model. Today, what I want to do is discuss transitioning this model to a symbol format, which we will use henceforth. So we will no longer build models by entering individual numbers. And RaRa spent a huge amount of time building into the 4NEC2 package the ability to write variables into the model of this old Fortran input. And what that enables you to do is sort of like, it's almost like its own language. You can assign variables, and once you do that, there are huge advantages. So this model is very simple, but if you want to change the length of the dipole, you have to change it in 2 places. And if you want this kind of precision, you have to type in the numbers correctly. But if you imagine for a moment a hex beam, which many of you may be familiar with, a hex beam has many, many, many segments, more than 100. And many of the segments are the same kind of dimensions. So typing, if you want to change a hex beam, if you want to tune it or change anything, it's really complicated to do it with a numerical model. Instead, if you had a variable that you could assign, you could change the variable once, and throughout the entire model, it would be changed, much like in C++ or Python or any of the normal programming languages. So basically, RaRa put this in place to help him in his more complicated models do many things, but the obvious thing is to make it simpler to change the dimensions and change variables. If you want to see the effect of, here I did not change the dielectric constant, but you could. You can make any of these variables, including the frequency, the lengths, anything you see here can be a variable that is assigned. So Voers, because he was doing a lot of modeling back then, he was very passionate about it. He built in this variable model. So let's see how that works. So if you want to turn your numerical model into a symbolic model, how would you do it? Well, first, you would definitely want to make the wires themselves all variables. And then any other aspect of the model that you want to change to explore, you can make that a variable as well, like dielectric constant, resistance, frequency, radius. Most aspects of the model can ultimately be reassigned as variables. So it's best to do the geometry part, the wires, on an actual visual part of the antenna. And I'll show you that in just a second. So how do we convert the model from numbers to a symbol format? We convert every wire coordinate to a variable representation of distance or frequency or angle or anything that goes into the model. And it's best to do this on a diagram. It is possible to do this in your head after a little practice of doing it on a diagram, but I find it still, even today, after doing this since like 2010, difficult to think in 3D. So often I draw the whole thing out. Wherever there is a wire, we change it to the variable representation on the drawing, and this helps to avoid mistakes. And then we go back to our model and we provide initialization of the variables and then convert the model to a variable format. So here is our flat top dipole, and now it's the same flat top dipole we had at the last class. We still have 3 wires plus a mast, so making up a total of 4 wires. The antenna part is 1, 2, 3 wires, the left leg, the right leg, and the center. And the coordinates, which are relevant because the wires are programmed with coordinates. The coordinates are 1, 2, 3, 4 coordinates plus the coordinates associated with the mast. Okay, so now I want to take these distances between these coordinates and assign them variables. Okay, so I'll start at 0 and work my way to the negative side for x. When I get to the first coordinate, this one right here, I will label it center offset, but since it's on the negative side, I'll label it minus center offset. So this is the little bitty wire in the middle, and it offsets from 0 just a bit. Then the next coordinate, I start with, I label the distance from this coordinate to this coordinate as x distance, and since it's on the minus side, it's negative. And then I label this coordinate, minus x distance, minus center offset. So this ends up being the total distance from 0 at this coordinate. Similarly, on this side, I have plus center offset. And then I have this x distance to the next coordinate. And here I have x distance plus center offset. So now I have these variables that represent these coordinates. So in the wire cards, I can go back in, assuming that I have assigned these, and I can replace the numbers with these particular variables. Also, auxiliary variables are mast height and center height, which are different. The mast did not quite touch the wires. And so with this, we also have one other variable that's important, end height. So for a flat top, we could get away by saying, okay, we're not going to have a separate variable for the height to the antenna. Okay, we're going to have center height be both of these heights. However, if we ever want to test a inverted V, we'll need the end height. So I have separately called this the center height, and then the end height becomes the edge of the flat top, which can now become, if I change end height to be lower, it can now become an inverted V. So I'm thinking ahead, trying to make this a flexible model. Okay, XYZ is 0 down here, minus x plus x. Okay. And this 30 feet is wrong, it's actually 31 feet. Okay, so now let's re-look at our model and rederive the entire model in terms of the variables that we assign. So let's start at the top. There's a comment. So if you would like to make a comment within the model, and you want it to be sort of in line with the model, then I use CM cards, which and then this text is just any description you want to put in here to remind yourself what the model does, because 3 years after you write a complicated model, you might benefit from writing a lot of things up at the top in comments. And then CE starts the whole process of reading the next part of the model. Now, the way you assign a variable to a number is just like when you're programming assignment variables in C++ or Python or in any particular programming language, MATLAB, whatever it is. So you declare it as a symbol, sy. You give it a string. Here in this case, I'm giving it frequency. You set it equal to the value you want this particular string to take on. So the frequency will be 14.35. We're going to have a 20-meter dipole, and this is going to be at the upper range, the phone range. Then you do the same thing for center offset. You say sy, center offset, equals 0.15. Sy, end height, equals 9.44, which is 31 feet. The center height in the middle is 9.44. X distance initially will be 4.9534. And then the mast height is equal to 9. These are all in meters. Okay, so we have assigned these. And now, having assigned them properly, we can use them. So in the first wire, as you recall, we have GW1, and this is the number of the wire and the number of segments. And then we have encoded the first coordinate with minus X distance. And if you recall, these wires are X, Y, Z, okay? And then X, Y, Z. So a complete wire is 2 coordinates, X, Y, Z of the left leg end, and then X, Y, Z of the left of 0 for the offset. So we have minus X distance minus center offset, which is all the way out to the far left. And let me just go back to, so here we have this X, Y, Z we're going to encode, and then we're going to encode this X, Y, Z in the first wire. So here's the first wire, GW1. X, Y, Z, sorry guys, X, Y, Z of the far left, and then X, Y, Z coordinate of the rightmost part of the left leg, and then we give it the type of wire it is, number 14. Or that's the radius of the wire. It's also a variable, but it's internally declared. Okay, same thing for the next wire. The center section is X, Y, Z. That's minus center offset. It's at the center height. Y has no value. And then we cross over 0, and now we're positive. And we have a plus center offset, 0, and center height, X, Y, Z. Same kind of wire diameter. And then the rightmost leg of the dipole is center offset, X, Y, Z, at the center height, to the X distance plus the center offset, and at the end height, X, Y, Z. So these wires, which formerly contained the coordinates in numbers, now contain the coordinates in variables. And once these variables are present, they can be used in many ways, and I'm going to demonstrate that here in just a second. Now, any of these could be put in, and I often do. I haven't done it here. I don't want to have an entire model in variables. It might be a little confusing the first time you see it. This load, any number you see can be encoded with its definition. And I have changed the frequency, which was way down here, to be way up here. So when I want to change it, which I often change frequency in these models, I can go right to the top of the model and change it, save it, and run it, and I'm done. I don't have to hunt all the way down to the bottom of the model and then type in a number. And I might type in the wrong number. So these are highly visible, easy to change, and they simplify the model once you get used to writing the model in a variable format. So any questions?
Yeah, this is Tim. I have a question.
You bet.
So this is my first one. I missed the first meeting, but I have the benefit of having sat through it last night, so at least it's all fresh in my head. But
Okay,
I have
good.
2 questions about the wire definitions. The first one has a 50 for segments, and the second one has a 3. Is that just an arbitrary number? Could you use 50 all the way through?
It is an arbitrary number, but there's rules for using. So given a certain distance, there's a minimum number. There is a minimum segment distance you can use. So if you put in too many segments, you'll end up making a segment too small. When you have a short segment, you don't need as many, when you have a very simple geometry, you do not need as many segments. When you have a short segment, you need fewer segments. And when you have a long segment, you need more segments. For this particular model, it's so simple. I could have put 3 segments for all of them and it would have been fine. But I didn't want to have them all be 3. Everybody would think, segments always have to be 3. So I will answer your question by specifically using your word. It's arbitrary within the rules of assigning the segments. And you don't have to think about those too many times when you're working on simple models. You only have to think of those when you're working on models like a hex beam, where you have these constant edges.
Got it.
In that case, you have to be careful to get each of the wires properly segmented so that all of the wires have reasonably similar, all of the wire segments have reasonably similar lengths. Here it doesn't matter because it's so simple and there's not too many curves and changes and things like that.
Okay, thanks. So then looking down at the exciter definition, it's using wire number 2, segment number 2. I didn't understand what the second 2 meant.
This is right here at the EX?
Yeah.
Okay, good. So if you look at the EX card, 0 defines what it is, what type of, it's a voltage.
Yep.
You can also use a current. Then this is the wire number 2.
Right.
Now we have 3 segments. 1, 2, 3 segments. Okay. This number is the middle segment. So I'm assigning the transmitter to be resident dead center of the antenna, dead center of the wire.
That's why the 3 needs to be an odd number in that case.
That is correct.
Got it.
That is correct. Now,
thank you.
Now, if you made this antenna with 4, you would get almost identical results. But to be formally correct, your observation that you want to have an odd number of segments where in the part of the model where you're going to place the transmitter is a good observation.
All right, thank you.
Because you want symmetry around the transmitter.
Absolutely.
And I had forgotten to ever say that, and I'm glad that you asked the question. Thank you.
And just one other point, in this definition, it looks like the mast starts on the ground. Shouldn't it be raised up off the ground?
So, yeah, this is what I want to say. Let's go back and look at our model. So I confused people last time And I can't remember if I was confused, but sometimes I am. But I know after the class, I realized I had confused everyone in the following way. So NEC 2 does not support parts of the antenna being in contact with the ground, okay, or below the ground, period. NEC 4 does do that, but NEC 2 does not. So if you have a vertical or any kind of antenna that starts at the ground and has a bunch of ground radials, then NEC 2 will not work. What will work is if you elevate them, and you'll learn a lot from doing that, and I have actually done that. But if you elevate them just slightly off the ground and elevate the antenna slightly off the ground, then you'll get an accurate result. Now, in this case, this mast is not part of the antenna. And I just put it in here to show you guys something later on, that it does take on current and it is excited and it does ultimately impact the model. Later on, and when we build, we're going to build a vertical that has 4 elements, 4 radials. And at that point, we are going to raise this up off the ground, because then we will care about the actual results of this being part of the antenna. But you can stick it in the ground. It's not going to affect anything here because these are orthogonal elements. And you can stick it in here and the model will run. In this case, it won't matter if it's up off the ground or not, because it's not part of the antenna, and because the actual antenna is orthogonal to
Right.
All right.
Okay.
So and your question is another great question, because the very, very first time I ever built a vertical, I was unaware that NEC 2 doesn't support antenna components at or below ground. So I put a bunch of radials in slightly below ground, and I sent out my results. And one of the senior members of my RDXA club, a guy named Jeff Ock, who is the most knowledgeable guy in many areas I have ever met. He thankfully didn't respond to the entire club. He responded just to me, and he said, "Mike, great work. I'm glad to see you're getting into this, but your model is wrong and it's giving you wrong results, because NEC 2 runs, but it doesn't support buried radials or contact with the ground." And if you Google search that, you'll find that to be true.
Okay, thanks.
But it will run, but I don't care in this case. So I don't think I said that last time. I think I said something more confusing. Keep all the wires up off the ground, while I built one into the ground. And so that was confusing.
Thank you.
Okay, so any more questions about this slide? All right, we'll move on. Now, with this model and this frequency, the frequency we are using aligns with the SWR minimum, okay? Now, having transitioned to this powerful format, how can we leverage it, and how did Ari Voers leverage it so cleverly? So here we have a model. If we wanted this antenna to be the lowest SWR at 14.35, we're done. We don't have to do anything else at all. But let's say, and I have been teaching myself to CW now for a while, let's say we grew up, in the 60s, we had time to learn CW. We can do 70 words a minute without even, we can make dinner and do 70 words a minute listening. Like there is a guy in our club, K2DB, who can actually talk while listening to 60 words per minute and then answer. And so if we're CW, and he will not use phone at all, he only uses CW. So let's imagine we're CW guys. We don't want this antenna to be tuned at the very top of the band. We want the antenna to be tuned near the bottom of the band, 14 megahertz. Now, if I have the model that we started with, let me go all the way back. If I have this model, the way I would find the new length is I would come in here and without knowing what to do, I would just type in a number here, type in another number over here, run the model over and over until finally after 20 iterations or whatever, I come with 14.0 megahertz, much as you would actually trim a real honest to God dipole over and over. And then unfortunately here, if I overshoot, I don't have to go get another wire and start all over. Okay, so now I want this antenna to function on 14 megahertz, and I do not want to laboriously change my model because I have a variable format. Ari Voers, he then coded into his basic infrastructure nonlinear optimization. And not only nonlinear optimization, a fantastically powerful one. I don't know how he found a free one. Maybe he wrote it from scratch. I don't know. The only optimization packages I've ever used were pre-existing Fortran models and pre-existing MATLAB optimization stuff. So I don't know how he did it. And the code is not out there. He has never released it, just the compiled version. But he built into Fortran 2 one of the most robust, powerful optimizations I've ever seen. So you can optimize a variable once you create one. So what we can do is we can change the model frequency to 14 megahertz and change nothing else, at least at the moment. Rerun the model, and this is important, and I'll say it more than once. If you change it to 14 megahertz and start doing optimization without rerunning the model, there is something I want to show you guys. There is something that can trip you up, and routinely, even now, still trips me up. So if you go to your C drive, you'll see that there is a directory that exists, or if you go to wherever your install is, and you will see, I don't know if you guys can see this. Can you guys see this little out directory? You can. Okay, good. All right, so this out directory contains binary information about your antenna, and if you change the model to 14 megahertz, this binary information still contains 14.35. So if you do optimization, sometimes these pre-existing out can confuse the optimization result. All right. Now there's a bunch of ways to get around this. You can close Fortran 2 and then delete this file, reopen it, and then type into the top the new frequency and then rerun it to recreate this. That's one way. And sometimes when I have a complicated thing I'm doing, sometimes I just clear this whole thing out and start again. But let me go back to my slides. By rerunning the model, assuming it runs, you update those binary files that are in that out file there. Now, those, if you're not doing major updates, those files are helpful because when you open your model, it's all the same as it was last time. And it shows all the results, and you don't have to rerun it every time you open a model. But sometimes it gets in the way, and I'll show you how it gets in the way. But anyway, and I did send all this information off to Ari, but he didn't fix it. Anyway, I do still communicate with him once in a while, but he's far away from it now. Okay, so we change to 14 megahertz. We run the model that updates the out file and all the binary stuff that's sitting out there with a memory. Now we run the built-in optimizer, and I'll show you how, and we select the length, the variable length. We now have a variable we can select that we desire to adjust. We run the optimizer, and we select a constraint, SWR, and that will minimize that constraint. And the optimizer in about 5 seconds will return the optimal length for 14 megahertz. And then all you got to do is copy it into the model and run your model. So let me go to the next slide. So these slides are going to demonstrate how you do this with Fornec 2. And then I'm going to live demonstrate it. But I wanted to actually demonstrate it in slides because it's easier to talk through something when you're not also doing something, which I learned last time. Okay, so first, leave the entire model alone and change the frequency. Run it for the far field pattern. And this will update that out file and the binary traits that are saved out there that contain all information of your model.
Excuse me, can you make it full screen? You know, get rid of the
yes,
left
I
side.
can. Yeah, my bad. Let me just see if I can figure this out. Yeah. Is that better? Sorry, guys.
That's better.
Yeah, I had looked in that directory and then forgotten to go back here. So thank you for pointing that out. All right, so now I rerun it. I wrote far field pattern. And this will just regenerate all of the antenna traits, gain, everything, and it'll encode the antenna traits in those binaries. Okay, once that's done, I go back to calculate. And if you go under calculate, in addition to NEC output data, which runs the model, I can start optimizer. So I start the optimizer, and that then enables this view. And this is when you first look at this view, it's a little confusing, at least it was for me. So over here, we select optimize. There's other choices, okay? And now you can see all of the variables that we put in here. The previous model, if I loaded it up and tried to do optimization, would show nothing here because there's no way to optimize a number that's fixed. But now these variables, you can see what they're initially assigned to. And if you come here and click on one, it will move over here and show up, okay, as X distance. This is the variable you want to optimize, and you can select more than one. Now, when you're working with a dipole, your best gain is also your best SWR. But you might have a beam where you want to optimize gain and SWR, much as some of these big, I forgot what's the name of that kind of beam that has a matching section on it. Anyway, there's a famous beam that has a matching section, and those guys optimized it not for 50 ohms, but for 12 ohms. So here we want to minimize the SWR. Now I could, if I had some more complicated antenna add, I can split this out. I'm going to put 100 here, but I could split this out to 25, 25, 25, and split the difference from all of these important factors, front to back, gain, etc. In this case, I just want to minimize the SWR because that'll be the point of best performance. Once I do put 100 here, so I select this, I put 100 here, and then I press start. And let me see if I missed anything to say. No. Then in front of your eyes, the model will run and it echoes out all of most of the information. It echoes out SWR. Okay. And this is at the end, so you don't see when it was high. And at the very, very end, when the model stops, it'll tell you how many steps it took and how much time it took. In this case, it was 5 seconds. And now I have a new length, okay? So this distance is good for 14.0 megahertz minimum SWR. Okay, before we go and put that into our model, let's look at something that pops out that you might not notice when you run the optimizer if you don't look for it, and depending on how busy your directory is. Because for the first year I did this, I never realized this particular file existed. Anyway, there's something called an optimizer log. And in the optimizer log, if you open that up, you have a record of all of the information, including where it started. Here's the SWR. Now this, I can't see the steps over here, unfortunately. I'm gonna have to go out of this view because wait. I see a way to get out of it. There we go. Okay, now I can see. So on the right, you see that we have an X distance 14.9562. For some reason, the optimizer comes out with SWR that's actually not correct, and I don't know the answer why. But now it starts through its steps with a specific resolution outcome, and it actually adaptively changes the steps. You can see in the distance, it adaptively changes the steps until it converges on a new number, and it prints that out down here at the very bottom. So you can see all of these 5.0854. So large amount of information is in this file. You can go back and you can look at, and later on there's a genetic evolver that also writes out stuff here. So it's really, you can see the step size starts out at 10. I'm not sure what it's doing up here. I am sure what it's doing up here. This, in his first two trials, is going slightly above and slightly below the optimal frequency that it's at. Okay, I see that. Okay, and then it begins trying to move towards the new optimal frequency. All right. So let me explain this again, since I was a little confused at the outset, and I apologize. So when this model starts, it's set at 14 megahertz, and 14 megahertz is not optimal. 14.35 is, so the SWR is 2 and 1.9, but I didn't initially quite understand what this is, and I haven't actually spent much time trying to sort it. But what the optimizer does is it takes the target frequency and it steps around it to give it 2 points, and from that it gets its vector direction. So if you ever have done optimization, it'll be some derivative that it looks at, and it calculates the derivative by getting these 2 points, and then it starts searching. So it knows it needs to go down in length. So it needs to go up in length. So it continues to go, iterate on the length, and as it gets closer, it adaptively refines this step size. So it's just your basic, very good, a nonlinear adaptive optimization. And where he got it, I do not know. I would love to have access to this code, but I don't think he's ever going to release it. And I'm not 100% sure why, since he's not trying to sell it. Okay. So now we take the distance from the optimization outcome and we put it into our model. Done. All right. And go back and regenerate all the output with the target frequency, 14.0 megahertz. Okay. And once we've redone the model, rerun it, we go into a frequency sweep. So instead of going to far field pattern, we select frequency sweep to check to see if the optimization worked. And it did. Not only did it work, it works perfectly. So we are lined up exactly at 14.0 megahertz. Okay. So now that was one section of this presentation. What I would like to do is go ahead and run the model, and you guys can ask questions as we run the model. But it's basically going to redo, it's going to redo what we've done. All right, and I don't want to close this. So I'm going to come over here to Fornec 2. I'm going to open it. I don't know which model is in here at this point. but it looks like the right one. Let me just take a quick look. Yep. Okay, so now we have this model. I guess I need to run it. Far field pattern is what I want to generate. Now, did you guys notice that the color was orange over here and now it's clear?
Yeah.
So when you have a model that hasn't been run or the out file has not been updated, it'll be orangish, brownish over here. That tells you in a visual that your out file needs to be updated. Once you rerun it, that orange color goes away and it's clear. So now you know that the model is updated with the parameters in the file, okay? In this case, there was just nothing out there, or whatever I left there yesterday is not the same thing as what's in the model. All right, so we have a far field pattern and we have 14.35 megahertz. Let's leave that open. And we're going to go back in to the model and change this frequency, okay, and save it. Now I hope to show you one of the challenges with making changes like this and then rerunning Fornec 2 so that you're not surprised by it, okay? So let's see. Calculate. All right, now you can see this brown here. I changed the frequency. Now the model in the notepad view is no longer compatible with the out file. All right. So let me rerun it again. Let me go back. Geez, guys, 1 second. I'm going to kill this. I'm going to go back to calculate, far field pattern. And now it's turned white. Okay. So you can see also that 14.0 megahertz is up here. So now the out file and the binaries are lined up and the optimization will be set up to run around those variables. Okay, so now I go for frequency sweep and I should see that it's still at 14.35, which it is. So now I'm going to go back in. Let me remind myself what the actual length should be. 5.0854. Well, no, actually now I'm going to run this optimization. Let me find, whoops. Calculate, start optimizer. Okay. And I can come up here until I find X distance. Oh, you guys probably can't see this too well.
No, I can see it.
X distance, I select it and it immediately goes to the selected variable column. I'm going to wipe this to 0. Now, if I don't put 100 here, it really won't give you an appropriate result. So I put 100 here and all you have to do is click. If you click, it'll go from 0 to 100. And if I click over here, that will also be equally weighted, but I don't really care about that right now because I know that the gain is going to be maximum at the lowest SWR. Now, I click this and off it goes. And 4.87 seconds. Today it's a little bit faster. And I have the same result, 5.0854.
Mike,
Yes.
can you say something about why you have XN also weighted at 100?
Well, so good question. So the answer is I probably can't speak to it intelligently. I can guess, but I'm not going to. So what I have seen is it's every time I've ever run this, it starts out like that. And I haven't explored what that is. And I'll try to do that this coming week and answer your question. But also, it might be, I mean, I don't know if it's answerable, some of this stuff in Fortnite 2, because there's no, but I'll take a look and try to answer your question next time. How's that? I will say it doesn't affect anything.
I know from running the dipole from our last assignment that the Smith chart plot tends down towards the infinity side on both sides of the axis, so that x equals 0 would be the lowest SWR in this case, even though it's 72, 73 ohms. But you can't make a general statement that the lowest SWR from a given impedance for some other characteristic impedance is necessarily at x equals 0.
I think it's trying to get rid of the imaginary aspect.
So so there's some of you guys who studied electrical engineering in college and worked at Harris, etc. So me, I'm a chemical engineer, and I have educated myself on impedance. I took one EE class, which was required, and I'm thankful for it. But I do not know why this isn't 0 or what it should be. And if you guys who have EE degrees, why don't we do this? Okay, I just ran the model, but I haven't changed anything in the model yet. So let's just take the class and let's explore for a second, which might slow us down, but that's okay. So I'm going to change this to 0, and I'm going to resume. So it'll start, because I haven't changed anything. Okay, so now it says 5.0719. So it does give a different result, but that might be fake because I didn't rerun the model properly. So let me come back over here. File, calculate. Let me redo the basic far field pattern. So I'm going to go back to where the starting spot is. Now I want to go. I haven't changed anything over here. Oh, I have. Wait just a minute. It'll take a second. All right, so I'm going to redo this to 14.35. All right. Now, this is where you see that there's a problem. You see this 14 megahertz up here? My model says 14.35. I did a calculation and 14's still there. So I got to do it again. No, that's just weird. So sometimes this happens, guys. So I'm still working on the same model. Let's try it one more time. Far field pattern. Okay, so let's do this. Let's kill this. Let's go here. I'm sort of glad this happened. And then I'm going to come here to the out file. I'm going to blow it away. All right, so now when I launch Fortnite 2, it's got no memory. And we have the correct frequency. So, gentlemen, this is what I fed this back to Ari like 8 years ago, and it's never been fixed. And the only way that if you're paying attention while you're doing various things and changing things, you have to be careful to make sure that what you thought you typed into the model actually is being picked up, because sometimes it's not. So now I'm going to rerun this model to give it the initial condition. Then I'm going to do I'm just going to follow the whole thing again. Generate. All right, I've got that. I want to go in here, change this to 14.00, follow our whole process, recalculate the result. Now that time it updated. Well, let's just see. See, yes, it did. You see that 14 right away it picked up. Okay, so let's calculate, give it the new stuff. And now we see that we're 2 SWR down at 14, which is not what we want. So let's go to the optimization. LPTI matching. Oops, that's not what I want. Start optimizer. Now, let's put in 0 up here. So all I got to do is click it. And let's select X distance. And let's see how it differs. .0718 compared to 5.0854. So there is a slight difference, and I can't tell you if that's because we're using a nonlinear optimization that starts with a random starting spot and then ends up at a slightly different result. So I don't know. I still don't know if this matters. But let's do this. Before, when we ran this, we got 5.0854. Let me write this down. 5.0718. And then the previous was 5.0854. All right, that was with 100. This is with 0. Now let's try both of them and see if it makes a difference, because it may not.
How about just closing the optimized dialog, hit OK.
Yeah, I can do that.
There we go. Now we see we got a -4 ohms on X in.
Okay.
And we see a 77.4 on the R in.
Okay.
Those are the two parameters that are going to change as you are changing the weighting on the X in.
Okay. So based on your understanding of what these are, where should we start? Because the program always starts at 100.
I think that's probably the most effective, most efficient.
Well, let's find out if in this case it made any difference. But so what, maybe I might email you or something to get a little bit more background, because I'm not fully understanding, RN and XN. That might be the impedance of the actual system at the transmitter. I'm not sure. So,
well, that's what we call the complex impedance. And I think that when we ran it before with 100% on X in, we ended up with an R in about 78. So that's okay. And then we ran a much lower X in, as I recall, when we ran it with the 100% on the optimizer.
okay.
So that's really just getting rid of a little bit of the phase angle on the impedance.
When you have 100 or when you have 0?
When you have the 100% on the X in weighting factor.
Gotcha. Okay, well, that's brilliant. I actually want to make sure I know who's speaking, because I can't see the people. I closed them. So
yeah, KA2CGB.
KA2CGB. CGB.
Yeah, Brian.
Brian. Oh, Brian. Gosh, dang, I didn't have your call sign. Okay, Brian, I should have known. Thank you very much. This, I learned something as part of this class. That's wonderful. So now let's see, practically speaking, for the simple, it may make a difference in some cases, but let's see what happens. We'll start out with 5.0854. 5.0854. All right. Now we'll calculate far field just to update the out file. Okay. That's always the first thing, and it actually worked. Like I mentioned, sometimes it doesn't. Calculate frequency sweep. So now it should be at 14, the minimum. And not only is it 14, I mean, it's perfectly at 14. So that looks really good. I'm going to take just this, well, I'll do that in a second. So now let's take the other one, which was 5.0718, and recalculate the far field. That's always the first step. You'll get a confused result if you don't. And now let's do NEC output data, frequency sweep. And the minimum is sort of flat between 14 and 14.05. I mean, obviously you wouldn't be too worried about this if you're building the antenna, but I do think that the previous minimum was more centered on 14.
It was actually the increment below 14 was the same as the increment of 14. So we've shifted it up just a wee bit, but I think really if we were to see the phase angle of the reflected, that's where it would come in. I don't know that this means a whole lot, but it would affect your matching network if you were going to be trying to transform that value to a different impedance.
Okay, well, hang on, because we're going to actually build a matching network to make this antenna work on 15 meters a little later. I'm not sure. Hopefully it'll be today. But at any rate, I definitely learned something. So I saw that 100 up there before, and having worked through a lot of stuff with Ari, I never asked the question. I don't know enough about impedance. I know what impedance is. I know what phase angle is. Obviously, I've done Fourier transforms and stuff. But when I saw that 100 up there, I just figured whatever Ari did was right, because I have yet, except for getting the out file issue resolved, where every time you rerun, you actually use updated variables from your model. He sometimes does and sometimes doesn't, but everything else that guy was right about. So I'm assuming it's not a bug in the program, but we can explore. I mean, you can explore that and tell us if it is a bug. We can feed that back, because he still does make updates once in a while. He really does. But he's far, far away. At any rate, practically speaking, and back to the course content, the variable format is how, if you are interested in doing modeling, which I do just for fun, and also all my entire system I built with modeling, and I looked at the effects, and some of them are pretty fascinating. And if you get something weird, you can check it in simulation and see, oh yeah, well, that's actually how it's supposed to behave. It's not some problem in my coax. At any rate, that, ladies and gentlemen, is how you use one of the many, many, many ways you use variables. You use you can use the built-in optimization. And I'll give a brief personal story. So when I built my 20-meter dipole, I decided not to use 468 because I hate cutting. So, in my case, I have to get it back. I have to raise and lower a steel pole. And even back when I was doing it, I was still having trouble. So I wanted to get it as close to right as possible the first time. So instead of using 468 cut and then raise and lower, I built, and it was above a 40 meter. It was above a 40 meter dipole, which had some interaction. So I put them both into the simulation at the right geometry and the right distances, and I ran both of them, and and it's interesting because the 40 meter dipole does affect the length as opposed to it's just sitting out there by itself. And I got the wire and I cut it just exactly what the simulation said. And then I put it on the mast and I pushed everything up. And ladies and gentlemen, perhaps partly because I'm using RG8X, it was perfect. The minimum was right where I wanted, perfectly in the middle of the band. And since then, I have validated all manner of SWR responses relative to my reality. At any rate, okay, now what's next? So that's an introduction to the variables and how to use them with this powerful optimizer. And it's unbelievable that Ari made all of this available for free. Universities use this. The universities in electrical engineering, where they're doing this antenna modeling, use 4NEC2, and they use it with NEC4 because of all this built-in stuff. I mean, I've always been so excited that such a powerful tool is so available. It just takes a little while to learn. Okay, where are we now? All right, so that brings us to the closure of the introduction to variables and one way to use them. Now, another way to use the variables is once you build an antenna in a variable format, you can change its configuration rapidly. Okay, you don't have to go in and change 100 numbers. So let's turn our flat top into a inverted V. Okay, and let's see how to do that using the variable format. Okay, to modify our model, we use the built-in text editor, basic Notepad. So I'm showing here, I think last time I mentioned use Notepad++. We were building the models, and I always build the models in Notepad++. But once the model is built, I edit the model in the regular Notepad that is part of the editing associated with Fornec 2. Now, you guys might be, for me, I've always been interested in using the symbol format, so I've never used the geometry editor or anything like that. For people who don't want to program or write variables or use the optimization or use any of the convenience associated with building a symbolic format model, there are other editors. We're not going to cover them in our course because one of the things I want to try to do is show how powerful building the symbolic format is, and you can look at it in the geometry editor, but it's why edit it there? Okay, so
just a quick comment, Mike.
sure.
I've been using the NEC editor new, the last one in this list, and as far as I can tell, you can do everything that you can do in your straight ASCII file in that editor. Symbols, optimization, everything. And it just cuts down on the frustration of getting the syntax just slightly wrong and then staring at your file for hours and hours and hours and trying to figure out what you did.
Okay.
So by using that editor, as far as I know, I have access to the full functionality of the application, but it does cut down a little bit on the complexity. And the learning curve is not quite as steep as when you just dive into the deep end and have to really take care of everything yourself.
Right. So what you just said is true. I do know the NEC editor that he put in allows you to assign variables, and then you can easily see them. It also makes it a little bit easier to view. It makes the whole process a little bit easier. However, for almost my entire career, I was programming in various platforms. And so I prefer to have access to every, I prefer doing it in a text editor or something, like Visual Studio Code or something like that, which is not useful here. So I use Notepad++, which has all this amazing syntax highlighting and power to search and things like that. So the Notepad edit, I recommend, or the NEC editor, I recommend, once you've built the model in Notepad++. And the only thing I want to say about Notepad edit is this. When you make a change and you save it, there's no going back. Notepad edit built into here has one step back. So if you make 5 changes and you decide those 5 changes are just wrong, you can only get back one of them without redoing it from your own brain. Whereas with Notepad++, and this is why I program the symbol format in Notepad++, you have a semi-infinite number of steps backward you can take. If you make 12 changes, you can step all the way back to where you were. So part of this slide is to talk about when to use Notepad++ and when to use either Notepad Edit, which I use, or the NEC editor, which is a nice clear form of the Notepad editing that Ari put out there for people who don't want to use the Notepad. And as Carl points out, It is very nice. And it has all of the power of the notepad. Okay, so now, summary. When you start out to build a complex model that's symbolic format, I recommend Notepad++ because of its search, its find, its replace. If you have, let's say you've defined a variable and you define it, and then that variable appears 14 times in your model. If you want to make all those changes really quickly, Notepad++ has a replace function where you can type in the variable, type in whatever it's new, type in whatever you want, and you can replace every entity of that string all at once. Okay. So that's it. First building, however, when making simple modifications. Okay, so don't use Notepad++ when you change frequency and then save it, because there are problems already with Fornet 2 recognizing Notepad edit updates, and they're worse if you use Notepad++ to do one-off updates and then run. Okay. Sometimes I've had complex models where I have to edit everything in Notepad++. And at that point, I just blow away the out. I close Fornet 2, I blow away the out file after updating everything, and then I restart and keep going, which is a pain.
Mike, you can bring that up to slide view instead of.
Yes, sorry. All right, there we go. Thank you. Thanks for feeding back, guys. It's useful and helpful. Okay, so we've talked about the out file, Fornet, the notepad, how to build the antenna at the beginning, and then how to update it. All right, good. Okay, so making and optimizing an inverted V with our new symbolic format. First, let's edit the model to make it an inverted V. Okay, and I'm gonna do, since it's not many changes, I'm gonna make the changes here. So because we have a variable here, end height, we can change it. If we made these two variables the same, then we would not be able to do that. So we can change end height and we can lower it. So let's lower it from 9.44 to 7. I picked that arbitrarily because it's visually obviously inverted V. And let's rerun the model. So we come back and we take the neck output data and we rerun it, and we get an SWR of 7.29. Now the reason for that is when we lowered the end height, the actual wire length of the antenna extended itself substantially. And we're very far away now from the optimal for 14 megahertz. Okay, so how do we get back? All right, we still want 14 megahertz to be the minimum SWR, but the wire length got way messed up because we're working. I thought I had a slide that went through that, but maybe not. So we're working, I do have a slide later, but we're working with the X and the Z variables, and we're not working with the wire itself, okay? So here's the inverted V dipole compared to a flat top dipole, and the inverted V is actually not too bad because we don't have a transmission line that's pushing through a 7.2 SWR. All right, so the gain is 6.2, which you guys might not be able to see. It's right up here for the inverted V, and the gain down here is 6.72. So there is some loss associated with the structure being at an SWR of 7.2, or maybe not. It could just be the inverted V, but you can't tell. Probably it's the inverted V, and we'll figure it out in just a sec. All right, so now we want to re-optimize our wire length so that 14 megahertz is still the optimal frequency. Okay, so we rerun the model, we start the optimizer, and we re-optimize in a few seconds, and you can see now this is really short. 4.5 feet, whereas before it was 5.0 feet. So this is shortened because we had to bring the end closer to 0 so that the wire length is now optimal. And we now have, previously we had a 1.52 or 1.56 SWR. Now the inverted V gives us a 1.379, which is a trait of inverted V compared to a flat top. It has lower SWR. Okay, so we take this 4.48 and we put it back in there. And boom, our SWR is now beautifully low at 14 megahertz. And we're still inverted V at 6.1 dB. So actually 6.1 and 6.2 are the same. So the high SWR didn't matter because we have the EX right on the antenna itself. And I'll show you guys, I have in these slides what happens when you put a transmission line in that has some resistance, but not yet. Okay, so now we've re-optimized and we have a real inverted V. It's optimized for 14 megahertz. And let's see what else. All right. But we don't have the wire length. Let's say we ran this simulation specifically to cut a wire and put it up in a tree. Okay, and we know from experience that using the simulator is way better than 468 divided by whatever. So, or whatever divided by 468. And anyway, now we need the wire length. So we come back and we type in, we just use geometry, and this is where I had the geometry. So this was the distance we optimized. This is the distance we want. And we simply do simple geometry here. And the total optimized antenna length is 34.45 feet, which should ring true to everybody. All right, questions about that? Just another way to use the optimization and variable function to reconfigure your antenna quickly.
Have you ever tried running the optimizer on the height variables of the flat top?
So let me go back to that model. Just 1 second. I want to make sure I know which variables you're talking about. So I don't know if you guys can see this very well. So here I have the variables, and the flat top and the inverted V both have the same variables, but this is the flat top version because the end height is identical. So you're now in the context of looking at these variables, re-ask your question, please.
Sure. I noticed that the inverted V SWR was lower than the flat top. And I was just curious. Now, of course, it would be a little bit more complicated to do an optimization here because we got the mast height variable. So we'd have to be adjusting both of them up and down as well. I was just curious if you know, since the inverted V had a lower SWR than the flat top, I was just curious as to whether you had looked at going up and down on a T antenna. Yeah.
Oh, I think I understand. So you're saying I created the inverted V by lowering the ends, which may, since it's closer to the ground, be why the SWR is lower.
That's the basis of my question. Yeah.
And so later on, we're going to do an optimization. We're going to rebuild this model where the wire itself is now a variable, and there's going to be an angle that we can optimize. And I think you'll find that very fascinating, and it'll answer your question about whether it's a trait of the antenna or whether it's an artifact of how far you are from ground. That's a brilliant question. And I actually have a model that we're going to use where we can answer that question.
Thanks a lot.
It's probably up there. Well, it's not in the current Google Drive that I sent out, but we'll get there. At any rate, so now, and that's a great question because, well, that's a great question because you're trying to separate out why is the SWR lower. But inverted V's, the ones like we just made where we lower the ends, they always do have SWR lower. Okay, back to the presentation. Okay, we calculate this length and we're done. Okay, so let me go in, since my plan was to demonstrate this stuff live. So we have this set to 14 megahertz. Yep. Now I'm going to change this guy to 7.0. I'm going to press Control S, save it. And now we should see the brown screen come up. Well, there is no screen, but so yeah, it didn't come up. There's nothing on that screen. So let's just calculate the far field pattern. Uh-oh, where am I? Generate. Okay, so now it took the update. We now have an inverted V. It's 7.11 instead of whatever. It's slightly different than it was. Let's actually take a look at it for a second, just to remind ourselves how to look at the far field pattern in this view. Okay, so now we can see the 3D view here of this guy. And we can move it around and do all kinds of stuff to take a look at it. And even better, we can come over here, grab this, move it next to it, move the mouse pointer over here, and then click on this, and you can see angle is 6.04 dB. Now, if you use the right arrow, you can go through all of your slices. Oh, and that's one other thing I wanted to show you guys. So these slices are 2.5 degrees, which I think is optimal for performance and analysis accuracy. So calculate. Whenever you run this, you have the choice here. I think the default when you install Fornec 2 is 5 degrees, which runs really fast on the older computers that Ari was working with. But with my modern computer, 2.5 runs in seconds. And I think 2.5 is better both visually and for looking at slices. So you guys probably all have yours set at 5 unless you've changed it. I keep mine set at 2.5. Okay, I had been trying to remember to say that. Okay, so back. So that basically, now we have run the model. We took a look at it. Let's go. We have edit. We've changed this, and we want to re-optimize so that we want to re-optimize the X distance so that our inverted V is still good for 14.0 megahertz. So let's go back to calculate, start optimizer. Now it's updating the out file. Nothing happened. Let's try it again. It worked. It recognized that we made some change. Okay. And actually, yep, we made that change. I'm going to go ahead and calculate the far field again to make that consistent. The fact that it's white now means that the out file is consistent with the model. You want to do that before you start optimization. Okay, so X distance. Now that's fascinating. Brian, take a look. It came up as 0 up here. Whatever I left it at, it saved it at. So I don't know. I'm going to leave it at 100 based on your analysis, but figuring out what that should be is interesting. All right, so I'm going to start the optimizer. Now I have 4.4842. I'm going to put that back over here instead of this. 4.4842. I'm going to recalculate far field. All right, and boom, we have 1.37 as the SWR. Let's go ahead and look at the sweep. Neck output data, frequency sweep. And it looks great. 14.0 megahertz, a little bit lower than previously. Doesn't get any better than this. Okay. All right. Now, we did the wire. Okay. So I've introduced you guys to building a model with numbers in the last class, however clumsy I did it. And we transitioned our model to a symbolic format, and we used the optimization capability, which if you don't ever use it for anything else for NEC2, that is huge power. But the amount of stuff you can do is just infinite. So let's do something that's not that uncommon and really helps out a 20-meter antenna. Let's say we want to have access to 20 meters and 15 meters, but we can only put up one antenna, which if you're in the city or even if you're just don't want to have a bunch of wires up in your backyard is a cool way of having access to multiple bands with a switch at your desk, or you can switch in a matching section. And so if you wanted to do that, in the old days, you'd have a bit of work to do. But with Ari Voor's implementation, he implemented into his code an automated network matching capability, meaning if I change, just like if I change the length and then use the optimizer, I can instantly get the new length. If I change the frequency and I use the network automated optimization, I can choose one of all of the kinds of networks, whichever one I want to use, whatever parts are in the basement or whichever one is the lowest loss for that frequency or whatever my preference is. The design, the electrical design is on the left. You know, you can choose, well, they're easier to see when you can choose an L network, you can choose a pi network, or you can choose a T network. And within each one of those, you can choose a low pass or a high pass. Okay?
Wide view.
Pardon?
Wide view.
Well, this is the wide view, I think. It's
No,
just,
wide, yeah.
oh, I see what you're saying. Here we go.
Thank you.
Yep, thank you. All right, so now you guys can see that in this, and it'll be better when I do the demo, and probably better in next slides. But Ari Voor's built this pane in, and then he built in, and I don't know how, he built in all the equations necessary to implement an L network, low pass or high pass, a pi network, low pass or high pass, and a T network, low pass or high pass. And even more, since these are two-port networks that are matrix algebra, he returns, whoops, over in this part that's blank, these, if you look at this, and actually it was probably 3 years of using this before I noticed this, the network card in NEC2 requires the matrix coefficients that mimic these actual networks. Now, coming up with those coefficients would require you to use MATLAB or something and invert the matrix and solve it. But Ari, when you click one of these and then run it, you get the result and all 6 coefficients show up here. And you can just copy those into the network card and then use them. And if it works, and sometimes, you know, if you have pushed it too hard, it might not, right? The matching section might not work out. But if it works out and you're happy with the simulation results, you can actually build it and implement it, which is huge. But you have to have the symbol format to do this, okay? Well, actually you don't. So let me take that back. You can do this in a model that's all numbers. and then you can build your own matching section. So this is sort of independent of the variable format, okay? So, and I'll say more about this as we go. So building a network to enable dual band operation with a switch at your desk, and then you can get low, as you'll see, you can get much lower angle of radiation and get local contacts using 15 meters. It's very different from 20 meters. So it's not uncommon for people to do this, right? And if you can build a little electrical network in a little plastic box and buy a switch, it's actually pretty effective. You just need, I mean, you don't even need a separate coax. You just need a little separate, you know, you don't need much except for the matching section. And if you can build it, this is awesome. So suppose we wish to use 20 meters with 15 meters. We add the matching network to the model, and then we optimize it. Okay, so let's take just a second before we throw this into the model to review the fact that you can always access what a network actually is, at least in NEC 2, by just Googling the network card NEC 2, and this will come up, okay? And then all the definitions are here, which we're going to go into in the implementation. The wire number, the segment number, oh, and this is important. So reading this is really important, and then understanding it is important, and then how to use it is important. But this says I1 and I2, which is wire number 1 and wire and segment, whatever segment you're going to launch the network from. And then this is the other wire and segment that the network connects to. So a network is a joiner between, let me go back to the previous. So a network has an input and an output. And in order to put this between an input and an output, you have to have a wire input for the input of the network and a wire output for the output, okay? And we'll implement that and I'll show you. Okay, let's go back. So reading this would make that clear after several readings, if I recall, for me anyway. Maybe Brian probably read through that, know right away. The 6 floating point fields, these are them down here. This is what you actually have to put into the model. And it's these values that RaVoors automatically returns. It takes 6 seconds to design a matching section for your antenna if you want to use it on 15 meters. And it'll take you half a day to build the matching section and test it and all that. But all of these coefficients, well, by the way, you can pick frequencies where a matching section just really has trouble or is really lossy and things like that. So it's, when you run the simulation, you can sort of see that through the radiation effectiveness and all that. But it just so simplifies your ability to build a dual band single wire antenna. Okay, these are the matrix coefficients of the 2-port thing, which I'll show you in a sec. All right, the network matching basics. A matching section is a set of impedance modulating components. When RF is passed through, it changes the impedance. You guys know that. Analog of a matching section is a network in NEC 2. A network is implemented into NEC 2 and accessed by the network card. To have a network, one must have an input wire for the input to the network, and then have an output wire, which is typically where your transmitter is. Or it doesn't have to be, but you have, as I'll show you how to do that, you have, yeah, I don't want to say it here yet. To have a network, one must switch the EX source between antenna wire and the network wire. So when the EX source is on the antenna, the network is inactive. And when the EX source is on network card, the matching section is active. a network exists between those two wires. You won't be able to see it, as I'll show you. And one that feeds the network and the other that connects to the antenna, whatever that's supposed to say. I think I've already said it. So we need to establish a new wire in our dipole model that serves to EX source feed the network card when we want it in use, okay? So this little wire is the equivalent of our switch in our shack or wherever your switch might be. The network then feeds into the former location of the EX source, okay? So let me visually show you guys what this looks like. So now we have our flat top dipole and we want to convert it into being able to use on 15 meters. And we want to do that with a network card, which we just read requires an auxiliary wire to feed the network. So our antenna remains identical, but in our model, we add a teeny little wire here that can serve as the jump off, and then the network will exist in between this wire and this location when we move EX to this wire. Okay, and I've got a picture that shows that. So now here, even if I have a network card in the model, it's not in use because the EX is directly on the antenna. Now, if I properly define the network card with this wire and this segment, and then as the target, this wire and this segment, now when I move the EX over here, the network will be in operation, okay? And I'll see its effect. Very briefly, I looked up two-port stuff, which Brian studied in college and may have done some at Harris. These two-port networks are just matrix algebra. It ends up giving 8 coefficients, but it turns out that because of the way they define admittance, it's a symmetric matrix, so you only need the 6 coefficients. All right, and I don't think I wrote that down, and it took me a while to figure all that out. Okay. And Carl, when he reads that, won't take as long because physics guys do that all the time. All right, so step-by-step building a matching section into the 20-meter dipole. All right, enabling a model to work on 15-meter with low SWR. Step 1, add an additional wire to the model that serves as the input to the network. Add a NEC2 network card, NT card, to the model. Comment both out initially. Run the model, which will result in high SWR for the 15 meters. It's interesting to see how high. After 4, go back and run the LPTI matching and use a high pass network. You can use whatever you want. I've found T high pass to be pretty common and they always seem to work over a wide array. I don't know enough about matching sections to know what's right for what frequency, so I use the T high pass. It works, and for this course, it doesn't matter. Just pick one. Then note the 6 coefficients that are shown automatically, automagically in this case, and if the SWR is low after you rerun, because you can use the matching section in the model before you implement it and see if it's going to work. As I'll show you. If it works, then you can add it to the model and it will be a permanent part of your model and you'll know all of the parameters associated with the model that you have to implement. Okay, so now what does this look like in our variable model? Okay, so let's start off with the most important part of it. Without this, another EX, okay, for the NT, hang tight, well, I haven't implemented both of them yet. We will see that. So this is EX for the wire, that little bitty wire that I showed you. We now have wire number 5, okay? So wire number, and here we go. Okay, so there's two EXs now. I've commented out one of them, the previous one, which was on the antenna. And I have put in one that is for the network card. And here is the wire for the network card. And I gave it a number and I gave it only one segment. All right, because I don't need a bunch of segments. All right, so that's the whole infrastructure you need to put into your model, a matching section. And let's take a look up here. This is the network card itself. The network card lives on wire 5, segment 1, okay? Oh gosh, I don't remember what these guys are. Oh, I don't, so my apology, we can look those, we can go back and look those up. And I will.
That's wire 2, segment 2. That's the place of the original.
Oh, yes,
feed point.
thank you. All right, thanks, Carl. So 5.1 is where the thing starts. So the network card includes which wire you start with and your target wire and segment that where the recipient of the network flow is. Okay, I don't know, getting 62 years old. All right. Now all of these coefficients, 1, 2, 3, 4, 5, 6 are the matrix coefficients associated with the network itself. Okay, that's it. That's all you need. You need a new EX, you need a new wire, and you need this card. 3 things. Okay, so now let's run our 20-meter dipole with 21.3 megahertz, which is 15 meters, okay, the phone band. And we find out when we do that, some interesting things. We find out that the SWR is super high. And you also have, because you're not using half wave or whatever on this antenna, you have some weird looking humps here in the current density, okay? All right, so now what do? We want to actually resolve this and put in a matching section. So how do we use 4NEC2 to do precisely that? First, you rerun the model or since we just ran the model, you don't have to, but if you haven't run the model or made any change, you run it. Then you launch calculate and LPTI matching, okay? And once you click that, you'll come into this screen, okay? L network, you actually can set someplace the queue. Trying to remember where I have set it before, I think. Yeah, here we go. All right, so you can set the queue that you want. It defaults to 250, but if you know that your system has a different queue, the final system you're going to build for the network, you can put that in. These are just placeholders. So these values for electrical engineers know what these are. I sort of do know what this is, and at one point I calculated it, but at any rate, these are adjustable parameters associated with these values, associated with loss. Okay, now you can click on these. These all have these numbers in here, right? 18.3 picofarad is the 2 of the capacitors, and then I guess this must be the inductor, 2.44 microhenry. So if you want to actually build this thing, you can order these, build this little thing, put it in coax, put it on a switch, and assuming your simulation showed that it'll work, it'll work. And depending on your queue that you put up here, it'll also show whether it'll be too lossy to bother with. Okay, but he doesn't calculate the queue because that's not, I don't know why, but that's not apparently possible. And most importantly for the modeling, here are the numbers you need to pay attention to. Now these we're not actually going to use these exact numbers because I ran this a bunch of different times and this is just one instance, but these are the the matrix coefficients 1, 2, 3, 4, 5, 6 that we put into the network card, and notice, well, these are actually all positive, but you have to be careful because these guys might be negative, and you have to get whether it's positive or negative, not just the number, okay? And in the model, I use capital E minus O3, as I'll show you. All right, so you click this, it turns green, that's the one you want. Now you click Use Network. And then when you click that, this pane will come up and it says Generate. Okay, boom. It runs the model with the network in place, and it tells you how effective the network is. And for reduction of SWR, it's phenomenal. Okay, and most of the time, this is how these matching sections work in here. Once in a while, you can get hosed up if you take it too far away from, you know, nature. Okay, so now we have, if you look at these numbers, these are going to be the numbers that we're going to put into our model. 1.92 E2 minus 3, if you remember that, you'll see that in the model. And I'm gonna show a slide where I show how to transport these into the model, but the actual numbers are gonna be different because the example was taken for myself years ago to remind myself how to do it. So now, after you run these coefficients, which are now not the correct coefficients, you take them and you put them up here in these 1, 2, 3, 4, 5, 6 places. That's it, just type them in. And in this case, some of them are negative. So you have got to get the negative sign correctly into the model. The J, obviously for the imaginary component, doesn't matter, just the coefficients matter, okay? All right, so now we implement our network. 1.92, E minus O3, 0.02594, each one carefully copied up here because it's really simple to not type them in correctly. And when we want to use this network, we have to comment out the voltage source on the antenna and uncomment the voltage source on that little fake teeny little wire that goes, in this case, from wire 5, well, EX default on the network feed. Yeah, wire 5, segment 1, and now wire 1. Does that make sense? Well, let's see what happens here. Maybe that's a problem. At any rate, we'll look at our model and see if that's correct. At any rate, my apology. Okay, so now when we put those numbers in and we properly configure the EX, we get the exact same result, and it's kind of interesting to look at. So if you look at the gain, you get a pretty big gain improvement by going to a frequency that's a lower frequency, and you get a much lower launch angle. So that's good for DX. And what's amazing is you also get a straight up component. So if you're interested in local contacts, the 15 meter will be good for both local contacts, or by that I mean, you know, Pennsylvania or whatever, and DX. So doing this and doing it in a way with a low loss matching network is pretty cool. Okay, and I just threw this in so to remind everybody that there's a 3D viewer that really allows you to make some nice diagrams and make beautiful, beautiful results. EasyNet, even at the end of its 25-year development cycle, never came close to this kind of graphics. And there's the network wire launch, and you can see we have the EX on the network, and there's no visual network in there. Okay, now one thing I want to point out. Wait, we're not there yet. Okay, that's the next section. Okay, so, or that's an accidental slide in the wrong spot. I don't know, but it's got nothing to do with the network. Okay, so now let's go back and let's do this ourselves. And I don't know what time it is. I guess we have about 15 minutes. Okay, so let's do this ourselves in our model. Okay. Now I'm going to come back over here. I'm going to go in here and edit. I don't have much to edit. I'm going to change this to 21.3. Press Control Save. Calculate. And of course, it didn't do anything.
You have 2.13 megahertz.
Oh, is that what I typed in? It still should have upped. Oh, you're right. That will be a little bit, it will still work, but it's not the, thank you. All right, so calculate. And it didn't work, so you just run it again, keep running it again. Finally, it works. And we don't want a frequency sweep. Okay, so now we have, well, this time we have 72.7, probably because something in the thing that I changed before is not exactly the same as what it was. But now we have SWR is 72, not far from 67, but everything else looks similar. And now we want to take this model and transition it to 15 meters. So we come back over here, LPTI matching. We can pick any one of these we want. We'll pick this one. It turns a nice, beautiful green and instantly gives us these parameters here. Let's see if they work. So we'll click Use Network. When we click Use Network, we get the same pane we get here everywhere. We want the far field pattern. We just want to rerun it with the network in place. And boom, now it's 1.06. So this network works for this application. So let's put it into the model. All right, so now I come down, well, this is not, oh, one moment, please, guys. Open, file open. I didn't transition the model. File open, oh my goodness. Okay, so now we want the NT version of this. All right, bear with me. So calculate far field pattern, edit input, make sure it's the network card version. Yep, and it's got the old, so I'm going to actually they're commented out already. The EX is
But
on.
this has the wrong frequency.
Yeah, it's the wrong frequency right now, but I'm just checking to make sure this is all correct. Okay, now we want this guy to be changed to 21.3. Okay, calculate. I used the wrong model, didn't have the infrastructure. Okay, now you can see, oh, this is 57.2, different yet. So calculate, we have that. Now we want to go into LPTI matching, select the same thing. Now we get all of these different coefficients, and these have to be transported over to here. All right. And I'm actually gonna do this to see how it works. Well, wait, no. I missed a step. Use network. Calculate. LPTI match. Oh, maybe I didn't miss it. Anyway, generate. 57.2. Yep. Okay, now I must have done. Hang on, guys. LPTI matching. Use network. There we go. It works. 1.05. All right. So now let's put this into the model. All right. So we're going to come down to here. And this is the first coefficient, which was formerly 1.92. We're going to put in 1.27. 1.27 E minus 03. This is the second coefficient. 0.02503, 0.02503. This is the third, and it can be tedious. That's the one in the middle, 2.41 E minus 04. 2.41 E minus 04. This is the fourth one, 4.27 E minus 03, 4.27 E minus 03. And then 4.65 E minus 05. And this guy is 4.65. Oh,
No,
yep.
1.32.
1.32 E minus 03. And save. Okay, so now the model's built in, but the infrastructure, and the infrastructure is, we're missing something.
You're going to remove the comment on the,
Yeah, we need to add this. Okay, and remove the comment.
on the NT.
Yeah. That's right. We need to make an NT and then, oh,
No, just to go up. Just go up and remove the comment on the NT.
The
oh,
line above.
so I need to make two changes. I need to put the EX on the voltage source for the network feed.
Which is
And
done, yes.
yep,
yeah.
that's the, and then remove this comment. And now the model should run our coefficients, and with any luck, it will look great. So I'm going to run far field pattern, and we've got 1.05. And let's look at the gains. And I'm going to press I, and it's the same. So we've got 8 dB, which is great, going straight up. We've got 5.87 dB, which is really good current going straight up. I mean, and it's broadbanded. So if you wanted an antenna that would cover the United States, local and far, this is it, in two directions. Or if you want to get Europe and then get locally up here in the Northeast. So it's not a bad antenna. And, exploring this kind of stuff can be exciting, and it can also shoot a lot of your weekends as you test stuff out that you learned in simulation. For me, it's just been tremendous fun, and especially since I've retired, I try all kinds of different things, and you can learn a lot just putting wires up in trees. Anyway, I'm not going to, let me see what the next section. So,
Hey, Mike, I have a quick question.
you bet.
Eric, so what does this use network? What does it do? Didn't quite follow that.
I didn't quite hear the question. Let me turn okay, ask the question again.
Yeah, so you press this use network. What does this actually do? Is it kind of applying that network card without adding it to the model, or what happens when you do that?
That's exactly correct. So
Okay.
when you say use model and then say generate, Vors in his if you had imagined a pipeline of things that he does in his code, he switches in an NT card, okay, into what your input is, because he's got it right. It's compiled down after you run the model, and he has all that.
Yep.
And then he
Makes
switches
sense.
an NT card in. He doesn't have to change the EX. Well, he does have to change the EX. And he makes all of that seamless, and you can take a look at it. In fact, a member of our club, I showed him all this automated stuff in Fornec 2, and he went back and he made a 160 meter antenna for his backyard that was teeny, and it had a big matching section at the bottom. And he designed it with this capability, which he works at Harris, and he didn't know it was there. So at any rate, there's so much cool stuff. But yeah, RaRa just switches it in, because you always get the same result as if you manually switch it. But let's say you want that model going forward. You don't want to have to go and remember what you clicked and all this stuff. If you just want a model with the NT card built into it, then you have to add it to your own infrastructure. But if
Okay,
you
thank
just-
you.
But the member of my club that used this, he did not add it to the model or mess with the model. He knows how to build all these different matching sections from his long experience as an EE. And he just got the parameters and went off and built it. And built the antenna that fits in, built a 160-meter antenna that fit entirely into his backyard, which was really cool. All right, so I think for today, let me just go over here and see what's next. Okay, I'll summarize. We covered some cool stuff. We covered the automation of both searching with the optimization and finding a matching section. And we covered doing some variables. I think we did a much better job moving through learning than what I did the first time. It looks like we also lost a bunch of students who were probably turned off by my initial approach, and that's too bad. At any rate, I just want to cover just a teensy bit about admittance and a question that that's next time. I don't know why that's here right now. Yeah, okay, so next time we'll do a transmission line and we'll make it lossy and we'll show how that impacts your antenna, both in gain and in SWR response, which is huge, okay? And we'll cover a bunch of other stuff too. We're gonna having done this model now in this way where we have X, Y, Z, and we made variables strictly in X, Y, Z. Next time, we're gonna convert this model into a trigonometric model where the wire itself is a variable that we can directly optimize, and then we can cover all kinds of really interesting optimization outcomes, and I'll show you guys which is the best. So the question is, you have a flat top, you have inverted V's, which one of those is the lowest SWR with the highest gain? And next time we'll do that.
One thing I'm hoping to learn is how I can feed my dipole with a 400, how I can feed my dipole with a 400 ohm parallel, what do they call it? Ladder line. So
Right.
hopefully that'll fit in somewhere.
Okay, I'll show you guys. So I have in my simulation an OCF, which is 200 ohm native. And I'll show you how to use 4NEC2 in a way that will give you the proper SWR. You don't need to implement it into a card, but I'll show that next time. I'll do that for my off-center fed dipole. Good question. And a very somewhat hidden, not really hidden, it's just not obvious that that's how you would do it initially, given all the complexity in the card format. So hopefully, guys, you come back next time. I enjoyed teaching this class. I enjoyed preparing for it. And I feel bad that I did such a bad job the first time that so many.
No, you didn't do a bad job. What happened is you presented stuff. This is great.
Oh, no,
Don't worry about it. This is
I was a little bit too much dead time. People probably thought they were wasting their time. Hopefully this time you guys, now here's some homework assignments. All right, here's a homework assignment. You have access to this 20-meter dipole, okay? And you have access to this 20-meter dipole with the NT card, and you got access to some other stuff that I thought I was going to cover, but didn't. Don't go to that stuff. So now, answer this question. Can you build a network that would make a 20-meter dipole work on 40 meters? And can you build a 20-meter dipole that'll work on 10 meters? Now, those are real simple things given that what we just did, but you have to implement a network card and you have to teach yourself how to switch it, okay? And then here is a really interesting question. For the flat top, explore how the SWR looks as a function of height. It'll take 5 minutes in the symbolic format to answer the question. If I put my dipole at 5 feet, 10 feet, 20 feet, 40 feet, 60 feet, 200 feet, how does it change? And it's just those kinds of things which are so fascinating to learn. And where is the best gain? Does the gain get better as it goes lower or higher? You guys already know the answer, but show it in the simulation. So that's it for today. And thank you for joining with this. I have a lot of fun, and I really appreciate Carl giving me the chance to teach this class.
Thank you.
Thanks.
Thank you, Mike, for doing this. I think we all appreciate this. And even though I played around with this for a little bit a few years ago, I still learn a lot by just listening to you.
Yeah, I'd like to second that. This is Jack, W2STM. I started doing this stuff in 1985 and went out to the postgraduate school in Monterey to learn it from the originators. But I learned a lot from you. I never really used 4NEC2, even though I had it on my computer. Now I will definitely use it. Thanks a lot.
Oh,
Yeah,
it's
great session. Thank you.
No problem. And I do want to recognize Ari Voers. He started in 1992 and he finally wrapped up in 2008. It was his passion. If he had not done that, we would not be talking, because EasyNEC does some of this, but not all of it. And this is free. Anyway, that's it. Take care, guys. See you guys next time.
See you next
Thank
time.
you.
This has been really great. Thank you, Mike.
Thank you guys for showing up.